In the previous video, we discussed we can use Laplace transform to solve ordinary differential equations. In this video, we'll implement it. We'll start by looking at the Laplace transform of derivatives. Assume we have equation lowercase y and perform Laplace transform to get capital Y. Then the Laplace transform of y prime is simply s Laplace y minus y naught. And for Laplace transform of y double prime, it is equal to s squared Laplace transform of y minus sy0 minus y prime 0. Both y0 and y prime 0 are the initial conditions. Let's set y0 equals to k0 and y prime 0 equals to k1. We can do simple substitutions. Then Laplace transform of y prime now equals to s capital Y minus k0, and Laplace transform of k double prime equals to s squared capital Y minus sk0 minus k1. Now let's look at the general form of second order differential equation. That's y prime plus ay prime plus by equals to rt. Apply Laplace transform on both sides. We can write it in the new format. The Laplace transform of lowercase rt is simply capital Rs. There is a mistake in my note here, which I will correct later. Note, before the Laplace transform, we work with the t space, so the variables are t. After Laplace transform, we work in the s space, so the variable will be s. Substitute what we had in green into the above expression. We'll have a new equation. Take out the common factor capital Y and rearrange this expression. Then take out the other common factor k0. You can easily write y as an equation of other parameters. Set 1 over s squared plus as plus b as the transfer function called qs. Some other books also express qs as h. You can write capital Y equals to qs multiplied by s plus a times k0 plus k1 plus qs rs. Then apply inverse Laplace transform to y. We can get the equation or expression for lowercase y. And this is how you can use Laplace transform to help you solve second-order differential equations. Let's look at a simple example. We have y double prime minus y equals to t. For the initial conditions, we have y0 equals to 1 and y prime 0 equals to 1. And we need to solve y. The most general form of second-order differential equation is y double prime plus ay prime plus by equals to rt. In this case specifically, we have a equals to 0 and b equals to minus 1, rt equals to t, and k0 and k1 are equal to 1. Let's start by computing the transfer function of qs. Again, I'm sorry about the mistake here. It's not qt, it's supposed to be qs. And qs equals to 1 over s squared minus 1. We also know lowercase rt equals to t. If we apply Laplace transform to make that into capital Rs, we'll have 1 over s squared. And here is just what we had from the previous page. Doing simple substitution of a, b, k0 and k1, you have a new expression. The first part is pretty straightforward. It is simply the inverse Laplace transform of 1 over s minus 1. The second part is a bit tricky. 1 over s squared minus 1 times 1 over s squared can be also expressed as 1 over s squared minus 1 minus 1 over s squared. The rest is easy. We just need to do inverse Laplace transform on these two terms separately. Checking with the Laplace transform table, you can get the final solution, y equals to e to the power of t plus sinh t minus t. In the next video, we'll look at something called s shift in Laplace transform.